I will present you a linear FPT algorithm to compute the connected path width of a graph. This is a joint work with Mamadou Kanté from University of Clermont-Auvergne in France and Dimitrios Diricos from CNRS and University of Montpellier in France as well. So let us start with some definition. A path decomposition of a graph is a sequence of subsets called bags of vertices that satisfies the following two properties. For every vertex, there exists a bag in the sequence containing that vertex, and moreover, the set of bags containing a given vertex V have to occur consecutively, like here in this set of blue bags. The second property is that for every edge, the two vertices of that incident to that edge have to occur in some bag AI. The width of a path decomposition is the maximum size of a bag, and the path width of a graph is the minimum width of a path decomposition of the graph. Here in this talk we are interested in connected path decomposition and connected path width. So a connected path decomposition, we have the following extra requirement of connectivity, which is that for every index I, the prefix here represented by the red bags, prefix AI, A2, A1, A2, AI, induce a connected subgraph. So all the vertices here together in the red bags induce a connected subgraph of the input graph. The connected path width of the graph is then defined as the minimum width of a connected path decomposition. To motivate the study of connected path decomposition and connected path width, we have to discuss a bit about graph searching. A search strategy consists in placing some searcher on a graph and removing searchers on a graph in order to capture a robber. So a search strategy is then defined as a sequence of moves. One move can be either you add a searcher, here you put a searcher on vertex A, here you put another searcher, second searcher on vertex B, or you can remove a searcher, here you remove a searcher from vertex A. At this time there is only one searcher present on the graph. We say that the search strategy is against an agile robber if the robber may move at any time along a path free of searcher. The strategy is monotone if no contamination is allowed, meaning that once you have put a searcher on a vertex, then in the future the robber will never be able to recontaminate that vertex. And finally, the strategy is a winning strategy if the robber cannot escape from its location at some step of the search strategy. The cost of the search strategy is the maximum number of searchers simultaneously present during the search strategy on the graph. And we say that the node search number against an agile robber is simply the minimum cost of a winning strategy. Now we are interested in connected path width, and so we will look at we will be interested in connected search strategy. Here the connectivity constraint is to guarantee that the guarded subgraph has to remain connected. So if I had a new searcher at vertex E, then I can observe that the subset of vertices that have been searched so far does not induce a connected subgraph. Thereby, this is not a connected search strategy. So a node search strategy is connected if for every I, at every step of the search strategy, the subgraph induced by the search vertices is connected. Why connected search? First, from a theoretical point of view, this is a very natural constraint that have been examined in a very different context. And also from the application viewpoint, if you think of cave exploration, maintenance of communication between searcher and so on, then the connectivity constraint is very natural. So what are the questions we can consider? We know that for the path width and the standard node search, I mean non-connected node search, the path width is equal to the node search number minus 1. So can we express the connected node search number as a width parameter? So second question is the price of connectivity. The third question is what is the complexity of deciding whether the connected path width of a graph is at most W. What is known about these questions? So for the first question, the answer is yes, and indeed with Isolde Adler and Dimitrios Tilikos in a recent paper, we formalized the fact that the connected node search number of a graph corresponds to the connected path width of the graph. About the price of connectivity, this is known from a few years now, due to Dereniowski in 2012. The cost of connectivity is at most 2, so meaning that you cannot, by requiring the connectivity, the path decompression to be connected, you won't increase the path width by a factor at most 2. And what is the complexity? Again, Dereniowski with two co-authors, Ursula and Żrawczewski, proved recently last year that this problem belongs to XP by designing n to the OW square time algorithm. Here in this talk we will prove that the problem is indeed in FPT, so we can improve the complexity. So let us discuss some possible attack. The first attempt is the generic approach of WQ, the generic WQO approach based on Robertson and Seymour work. What we know for the path width, if you want to decide whether the path width of a graph is at most W, we know that the path width is closed under minor. We also know by the work of Robertson and Seymour that graphs are well quasi-ordered by the minor relation, and also that minor testing can be performed in FPT time. Using this machinery, we can we can prove the existence of FPT algorithm, that is an algorithm running in time f of W times polynomial in n, where n is the size of the graph. Unfortunately, in our case of the connected path width, we don't have the parameter connected path width is not closed under minor. If you take this example, if you consider the graph with the edge x and y, then the connected path width is 2, without this edge xy, the connected path width is 3. So this is not closed under minor. We can prove that this is closed under contraction, but unfortunately we don't have the well quasi-order result for the contraction relation. Second attempt could be using monadic second order logic and Courcelles theorem. Why? Because the connected path width is larger than the path width, so we may assume that the path decomposition, that we have in hand a path decomposition of bounded widths, and then if we could express the connectivity constraint in monadic order second order logic, then we could apply Courcelles theorem. Unfortunately, we don't have a solution for this yet, so this third attempt is the standard dynamic programming approach, and using the typical sequences that were introduced by Bottlander and Klocks in 1996 in their paper to decide whether the path width is at most some W. So what is a typical sequence? A typical sequence is you take a sequence of integer, like here, 4, 6, 5, 7, 3, and so on, and you are interested in the tips of the typical sequence. So the tips are the first and the last point, and the highest local point and the lowest local point, meaning that between two consecutive tips, for example this one and this one, all the intermediate values are lying in between the two tips. So you can compute the tips of an integer sequence in polynomial time, and the subsequence induced by the tips is called the representative sequence. So we will use this technology introduced by Bottlander and Klocks, and on the top of this technology remain the challenge to represent the connectivity constraint. And I will now explain how we handle this issue. Okay, so, but before, the general approach will be you have a given graph, and for this given graph, you also have a nice path decomposition of width at most k. And you will, so nice path decomposition means that every bag is either an insertion bag or forget bag, which means in insertion bag you add a new vertex, in forget bag you just forget one vertex from the previous bag. This is some standard definition. The trick here is that you may observe that the prefix graph gi induced by the bags b1 to bi may not be connected. So we have to define what will be a connected path decomposition of a rooted graph. Here, this graph gi will be a rooted graph with bi, here the red bag, being the set of boundary vertices. So, a path decomposition of a rooted graph gb, where b is the set of boundary vertices, is a path decomposition ai to al with the following property, that for every prefix, again, if you consider the subgraph gj here, this the subgraph induced by all the vertices belonging to bag a1 to aj, then every connected component of this graph gj intersect the boundary set b. Here, this red subset of vertices. Okay, so now we need a tool to represent the connected path decomposition of a rooted graph. To that aim, we introduce the notion of boundary sequence. Boundary sequence is an object that does not correspond to graph anymore. This is just about a set B that we'll call boundary set. So a B boundary sequence is a sequence S1 to SL of triples, and each triple is formed by the first component BD of Sj, which is a subset of the boundary set. Okay, with the property that for every x belonging to the boundary, the indexes, the triple containing that vertex x, that element x in its boundary, form an interval. The third component, val, is just positive integer. And now the second component, and this is where we will represent the connectivity constraint, is a near partition of the subset of the boundary, the subset of B, which is the union of all the boundaries in the triples I smaller than j. Okay, so a near partition is a partition where you allow multiple occurrence of the empty set, and you require the property that this CC values, CC near partitions, are nested from one triple to the next one, meaning that every part of CC of Sj is contained in some part of CC of Sj plus 1. Well, now we can define the width of B boundary sequence as the maximum of the size of the boundary Sj plus the value of Sj. And we say that the boundary sequence S is connected if for every I the CC component is a partition and not a near partition, meaning that there is no occurrence here of the empty set. Okay, how do we encode a connected path decomposition of a boundaried graph with a B boundaried sequence? This is fairly immediate. The boundaried set Sj is simply the intersection of the bag Aj with the boundary set of vertices. Okay, the value Sj of Sj is the number of vertices of the bags Aj that does not belong to the boundary set of vertices. And now CC of Sj is simply the intersection of every connected component of the graph Gj, the prefix graph, with the boundary set P. So here, in that case, CC of Sj will correspond to these red subsets. Okay. Now we have to, the problem is that a boundary sequence can be arbitrarily long, and there can be too many boundary sequences. So we will need to compress them, and in order to be able to bound the number of B boundary sequence of width at most W. So to that end, we define the breakpoints. There are three types of breakpoints in a B boundary sequence. The first type corresponds to the position, the indexes where the boundary sets Sj differs from Sj minus 1. So for example, here, this is a type 1 breakpoint. The second type of breakpoints correspond to the indexes where the CC component is changing. So CC of Sj is different from CC of Sj minus 1. So for example here, you can observe that this partition of Sj, this near partition of Sj is coarser than the near partition of Sj minus 1. And finally, type 3 breakpoints. This is where the typical sequence are used. Type 3 breakpoints are defined by considering between two consecutive type 1 or type 2 breakpoints. So for example, here, we consider the integer sequence formed by the values of the triples, 3, 4, 5, 3, 4, 2, 3, and you will consider the tips of this subsequence. And so type 3 breakpoints is one of the tips. Here with the gray dots, these are type 3 breakpoints. And what we can prove is, so we define the representative sequence rep of S by the subsequence induced by the breakpoints of type 1, 2, or 3, and we can prove that the number of representatives is bounded by the width, by a function of the width of the sequence. Okay, but as I told you before, a B-boundary sequence is not a graph, and we have to link B-boundary sequence to graphs. Of course, we can represent a path decomposition with a B-boundary sequence, but not all B-boundary sequences correspond to a path decomposition. So we say that a B-boundary sequence is realizable in some graph G, in some B-boundary graph G, if there exists an extension of S, meaning that you can duplicate triples, elements of in the sequence S, such that this extension is encoding a path decomposition of the B-boundary graph G. And now, the set of representative of G, representative of width at most W of G, is the set of representative of B-boundary sequence of width at most W that are realizable in the B-boundary graph G. As I told you, this set is the size of this set can be bounded by some function of k, and this is very important for the FPT algorithm. But it will be too complicated to be sure that we compute, we maintain the set of representative. Instead, we'll maintain what we are used to call a domination set, which is a subset of the representative, such that for every representative there is one element of the domination set that dominates. So the domination relation, I don't have time to enter into details, but the domination relation is defined by means of the typical sequence. And finally, what we have is that the connected path width of the graph will be at most W if only if the domination set of G is non-empty. So now let's describe the two routine of the algorithm that are first the forget routing and then the insertion routing. So keep in mind that as input you have the graph together with a nice path decomposition of the graph. So for the forget routing, this is fairly simple. For this we define the operation of projection of a boundaried sequence, of a B boundaried sequence, onto a subset B prime of B. And the triple of this projection are defined as follows. So the boundary set of Si projected on B, restricted to B prime, is simply the boundary set of Si intersection B prime. Now, the value integer of Si restricted to B prime is the value integer of Si plus the number of vertices that we forget from B. Here, as we will forget only one vertex, that will just every time it will be a +1. And finally, the CC component. If CC of Si is x1 xs, is the set x1 xs, then CC of Si restricted to B prime is defined as the intersection of x1 with B prime of xs with B prime. What is the forget routing? So the forget routing is simply you take every B boundaried sequence of the domination set. So this B boundaried sequence is a representative of some B boundaried sequence, and you apply the projection of this B boundaried sequence S onto B minus X, and you check if this projection provide you a connected B boundaried sequence. If this is the case, then you add it to the domination set of G where you have forgotten X. And this algorithm run in FPT time, 2 to the O of k times W plus log k. Now the insertion routing, we first have to define what is a valid insertion. So we want to add one vertex, and we add a vertex with respect to a subset X of B. And we say that valid insertion position Fx, Lx, which correspond to the indexes in which you will add the vertex X in the boundary, they have every element of capital X has to belong to the boundary of some index between Fx and Lx. So now the trick is to compute the three components. For the boundary, this is simple. This is just what I said. If you are in the interval, you add the vertex X. If you are not in between the two insertion index, so this remains the same. The value also components remain the same. For the CC component, then there is a bit of work, because when you add the vertex X, then you may merge different connected components of the previous CC. But okay, you can perform this in polynomial time. It's not a problem. So what is the insertion routing? So again, you pick B boundaried sequence in the domination set W, and for every valid insertion position FL with respect to your X, which will correspond to the neighbors of the vertex you are inserting, you have to consider, and this is the key point of the algorithm. You cannot work directly on the B boundaried sequence S. You have to consider extension of S, extension R of S, that are obtained either by duplicating the index F, the triple SF, or the triple SL, or both. And then you insert X in this extension, in this at most 2 extension of S. And of course the connectivity, by inserting a new vertex, the connectivity is still maintained. But if you have to control the width, so if the width is still lower than W, then you can add the representative of the new sequence Sx to the domination set. And again, you can perform this insertion in FPT time with respect to K and W, where W is the expected width and K is the size of the boundary set B. So all in all, what we have is we obtain an FPT algorithm running in O to the W square times n, and we may remark that the quadratic dependence in the exponent here is only due to the construction of the initial path decomposition. The algorithm can be turned into a constructive algorithm by using a technique developed by Führer in a recent paper in the context of deciding whether the path decomposition of a graph is at most W. Okay, so let me conclude by some conjecture and thought about what should be connected tree width of a graph. So a tree decomposition is connected if we can identify a root, here this bag R, such that for every bags, the path between the bags V and the root R induce a connected subgraph. Okay, in the context of the path decomposition, the root bag R is one of the two extremities of the bag of the path. Okay, so here you fix one root and you request that every path between a bag to the root bag induce a connected subgraph. And again, you can express this as the connected path width, the connected tree width as a Cobbs and Rober game. And so this is a very interesting parameter to be studied. And what about the computation? Connected tree width at most K, can it be solved in XP time, which is n to the f of tree width of G? Or can it be solved in FPT time and f to a function of K and the tree width, where K is the connected tree width, times n, linear FPT time? Or is this in XP with respect to K, the connected tree width, rather to the tree width? Of course, the connected tree width is larger than the tree width. Well, so what do we know about these three conjectures? First, there is some hope for the first conjecture. The reason is that recently, with Guillaume Meskov, we designed a polynomial time algorithm to compute the connected tree width of a graph of tree width at most 2. So basically series parallel graphs. So this is compatible with this type of complexity. Okay. What about the second conjecture? Is the computation of connected tree width FPT? The EMSL expressivity of the connectivity constraint will not help as the price of connectivity is unbounded. Okay, even for series parallel graph, we know that series parallel graph for which tree width is at most 2 can have unbounded connected path width, connected tree width. So this is really not clear, and the other argument is here in the polynomial time algorithm that we have observed that we are not linear time algorithm, and honestly I don't know how to improve this complexity now to linear time. So to be compatible with this type of complexity, we should be able to have a linear time algorithm to compute the connected tree width of a series parallel graph, which is not the case yet, at least. Finally, the third conjecture is the weakest one, and we definitely believe that this one is true. But of course, we would like to prove or disprove one of the first two conjectures. Thank you for your attention.